Okay, I wanted to show you a second example of these differential rate law problems. This is one that a few people have asked about over the last couple of days, and I know a lot of you maybe are still working on it, maybe haven't given it haven't had a chance to try it yet. So I just wanted to make sure that we went through this one for the benefit of everyone who maybe hadn't seen it done yet as part of a in-class or an online connection when I went through it and you were there to hear it firsthand. There's not a whole lot different about this one at first glance necessarily, but there is something kind of unique that happens in this. Actually, two things that happen in this compared to the last one that I went through and posted already. So just want to work through this one with you as well. It's going to ask us to do the same things in this one as it did in the last one. We want to figure out the order of the reaction with respect to each reactant, and those we're given here are X and Y. We're not given a whole lot of information about this reaction as far as an equation necessarily, but the initial concentration of X here is given, so that's one of our reactants, and the initial concentration of Y is given. Those are reactants, and then it's telling us that Z is being formed by this reaction. The rate data that's given is the formation of Z. That's all we really know for sure. There might be more involved in this reaction. There could be other reactants. There could be other products. But as far as we know, this is the basic truth of the reaction. X and Y are reacting and Z is being made. And that's all we need to know in order to figure out the stuff that they're asking us to solve here. So the order of each reactant. We want to do what we did in the last one. We want to try to find two trials where something's held constant and something else is changing in a clear way. And so if I look at that, I'm going to look at trials 2 and 3. In trial 2, X is 0.4 as it is in trial 3. So this is being held constant between those two trials. Meanwhile, Y, concentration of Y, is not constant, obviously, and Y is being doubled. So from trial 2 to trial 3, the concentration of Y is doubling. What's happening to the rate as a result of that doubling the concentration of Y? And if we look at the rate, we see that the rate is doubling as well. So as Y is doubled, the rate of the reaction is also doubled while X is held constant. And hopefully we recognize that would tell us that the reaction is first order with respect to Y. The reaction is first order with respect to Y because a doubling of Y leads to a doubling of the reaction's rate. And so with respect to Y, and remember when we use that phrase with respect to, we're saying with respect to this thing that's being changed and causing a change in the rate. So with respect to the concentration of Y, the reaction is first order. And the way that we know that, because doubling the concentration of Y doubles the reaction's rate while X is held constant. And that little part at the end is pretty important. Because if X was also changing, we'd have potentially two different things impacting the reaction rate, and we wouldn't immediately be able to tell which one's responsible for the change in rate that we're measuring. However, here comes the twist on that. What if we have to figure out now what the reaction order is with respect to X? And if we look at that, what we've been doing is we find, in this case then, two trials where Y is held constant. As you look at Y, obviously there aren't two trials where it's held constant. Y is changing and is different in each of the four trials that we have data for. So then what? Well, the best thing to do is to pick two trials where Y is changing and X is changing in a way that we can kind of manage, something that's not too complicated. So if I chose trial 1 and 4, we have a Y changing by a factor of 6. That's big and complicated. We have Y changing by a factor of 4 between trials 1 and 3. Well, let's keep it simple as we can. From trial 1 to trial 2, Y is being doubled. And we know, without looking at anything else, based on what we just talked about, that the reaction is first order with respect to Y. That means that doubling the concentration of Y here, this should, all by itself, this should double the reaction's rate. Having a little trouble with my pen. Double the reaction rate. We've determined that because it's first order with respect to Y, that doubling Y should double the rate. This alone should double the reaction rate. All right, keep that in the back of your mind here. What else is happening in this reaction, these two experiments rather, is that X is being doubled. So we're also doubling X. And so the question really is, we know the reaction rate's going to double because we're doubling the concentration of Y, but what additional increase in the reaction rate do we observe that we can say is due to the doubling of the concentration of X, as we're seeing is the case here? Well, to answer the question, we have to look at the rate. And if we look at the rate for trial 1 versus trial 2, that's a simple doubling. The reaction rate is simply doubling from trial 1 to trial 2, which we have to credit completely, okay, to the doubling of the concentration of Y, because we know from the data that I have marked up here in red that the reaction is first order with respect to Y. Doubling Y has to double the reaction rate. And so as we double it in this example, that's going to have to cause a doubling of the reaction rate. This is due to the increase in Y. And there's no additional increase happening based on what's happening with X. The whole doubling that we observe in that rate data is caused by the doubling, or credited to the doubling of concentration of Y. And what that means, and we'll do it in blue here, because doubling the concentration of X while Y is doubled leads to no additional increase in rate. Adds nothing more to the rate, to the reaction rate in terms of an increase. We must know, and we can figure out then, that this reaction isn't at all dependent on the concentration of X. We could double X and it didn't do anything extra here. We could triple it. It wouldn't do anything extra here. So the reaction is what we would say zero order with respect to X. When doubling a concentration or tripling a concentration of something causes no measurable change in the reaction rate, then we say that it's zero order with respect to that substance. And in fact, if we kind of look here down the rest of the data table, okay, I'm going to clear that out just for kind of purposes here of cleanliness, I guess. As we look at the data here in the data table, we see that the concentration of Y is being doubled, is being taken times 4, is being taken times 6 as we look at the 3 trials. And likewise over here, the rate of the reaction is doubling, and then times 4, and then times 6. So those two things are a complete match with each other. And meanwhile, in the middle, X is changing from 0.2 to 0.4, and then it's staying the same, and then it's 0.6. And none of that has any additional influence on the rate of the reaction. So X's concentration isn't part of the story. X's concentration isn't part of the rate law expression either. And so as it comes time to write out our rate law expression, we would say that rate equals K times the concentration of each substance with its appropriate order for that specific substance. We figured out Y is a first order reaction, or a first order relationship, and X is a zero order relationship. Now, X to the 0 and anything else, of course, to the power of 0 is simply 1. So we can leave that out. We could say that the rate law expression is rate equals K times the concentration of Y to the first power. And that's it. Either one of these would be mathematically true, but the most concise way to do it is the latter one of the bunch. Okay. And then lastly, to figure out the rate law constant on this, to figure out K will simply be rate over the concentration of Y for whichever trial we choose. And so, I don't know, choose the last one. We haven't really used that last row at all in our previous work, so let's use that last one. The rate in that last row of our data table is 4.2 times 10 to the negative 3. And what are the units on that? Molarity per second, all right? So that's molarity per second. And then the concentration of Y in the last trial is 0.6, and that's moles per liter. 0.60 moles per liter. As far as our answer goes then, we punch that in and we can get our answer. I didn't punch that in advance, I apologize. Let's get that real quick. 4.2 times 10 to the negative 3 divided by 0.6 gives us 0.007. And we'll go with 2 sig figs because we've got 2 sig figs. But the units on that will be, molarity is going to cancel, seconds to the negative 1. So there's our K value. K is 0.0070 seconds to the negative 1. And that's my rate law constant for this particular reaction based on the data that we were given. And so there's kind of a lot going on in a table like that. It's a simple looking set of data, but when we have to sort of manage two things changing at once, where Y was doubling and then X was also doubling, you have to sort of be able to credit the change in reaction rate to each of those things separately. And the way that we can do that is first start with a substance where you can hold something constant and determine what its relationship was. And that's what we did here. Figured out that Y was first order because we had a pair of trials where X was held constant. and that allowed us to find that y was first order. And then with that in mind, we were able to take it a little further and say, okay, if y is first order, then what additional impact is the doubling of x having on the reactions rate in trials 1 and 2? And the answer was it wasn't having any effect at all. So that's a zero order relationship for x to this reaction rate. Hopefully that makes sense to you. If you have questions about this or any other questions in this section, feel free to email me or drop in on office hours, and I'll talk to you then. Thanks.